line integrals, which should be called, what would you call them, curved integrals? I don't know. We're not integrating over just lines, we're integrating over curves in this section, but they call them line integrals. So the goal is basically just to set up and evaluate line integrals. I'm going to tell you what they're used for as well along the way, but our goal is mechanical. Our goal is to set these things up. I need, before I define what a line integral with respect to arc length is, I need you guys to recall the arc length formula. So, I mean, this is going back to like the second chapter, right? And unfortunately, the thing about math is you forget it like a week after you use it, right? So a little bit of review here. So I'm drawing this curve in the plane, but it also applies to curves in space. So this could be a curve, call it C, and let's say it's one parameterization for it is r of t, whatever that happens to be. So a vector valued function. And let's say we start at point A, and imagine a particle traveling along that curve. T usually stands for time here. It doesn't have to, but it usually does. So imagine r of t given the position of a particle at time t. And we're parameterizing it so that we're traveling kind of in the, I guess it'd be the northeast direction, so kind of this way, right? So how would you measure the arc length, the distance if you were a bug or a particle traveling along this path from A to B? What formula gives us the distance traveled from A to B? So it was an integral, right? From little a to little b. You remember what it is? Anybody? Something. I know.
It's r sub t, sorry, the derivative of r sub t.
Okay. So magnitude, right? Magnitude r prime of t dt.
Yes.
Math, as you guys know, is very perishable, right? You've got to be in a constant state of review. So now, and since you have the final coming up anyway, now is the time to go back to what was chapter 13 for most people. If you have some editions, it's chapter 12, depending on what book you have. But it's the chapter on vector valued functions, right? So go back, start reviewing this stuff if it seems like a foreign language at this point. But that was a good attempt for not having looked at it in a couple months. So, and what did we call this? We just called it S, right? S stood for that length of arc from A to B. Remember that? Okay, now, what's the little a and little b in relation to the uppercase and uppercase A and B? Well, this point, uppercase A, would be given by R evaluated at t equals lowercase a, right? And this point, which we're calling uppercase B, would be R evaluated at t equals lowercase b. I mean, that's not what it has to be from the integral, but that's what we're assuming, okay, to set up the integral. So it's kind of the other way around. Okay, so that integral gives us arc length. Now, does anybody remember another name for the magnitude of r prime of t? In terms of the arc length parameter s. So we had a related function s of t where we made that top limit, we made that a variable, remember that? And then we replaced the t inside the formula with a dummy variable u. We called it the integral from a to t of the magnitude of r prime of u du, and we called that the arc length. We call that s of t the arc length function. And magnitude of r prime of t turned out to be ds dt. Does that ring a bell? Okay. Now, you guys know we're very informal here. I'm not going to set up a Riemann sum and prove all this, but I will say that what you would expect to happen with the differentials does happen. So that if you were to rewrite this thing, ds, so you'd have the integral a to b ds dt dt, that would be the integral from a to b. dt's cancel. I hesitate to use that word because what the heck does that mean? And we could rewrite this integral as just the integral from a to b ds. And if we have a non-specified parameterization, we use the notation just the integral over the curve c. ds. So it's like we've invented a new integral with an integrand of 1. Now, what does it mean when you say the integral over c of 1 ds? Well, it's just the arc length from the beginning of the arc, which is uppercase A, that point on the curve, uppercase A, to uppercase B. It still means the same thing it did using the previous notation. But I'm going somewhere with this. So it's like we invented this new arc length integral. Is there any reason why we really have to keep the integrand equal to 1? For simplicity's sake, well, sure, but why would we want to be simple? Let's stick a function in here. Stick in a function. Again, this is a very informal development. In a more advanced class, you're going to be talking about Riemann sums at this point. And you stick in a function, and guess what? You create an integral, arc length integral, and it's a brand new integral of kind of, but we're going to turn it into just a single integral of the type from Calc 1 when we actually evaluate. So anyway, that's where we're going. So let's define the line integral with respect to arc length. So again, we have an underlying c and a parameterization r of t. C is at least a piecewise smooth curve here. So it's pretty well behaved, no sharp edges or a finite number of sharp edges if it's piecewise smooth. Then we would have something like this. The integral over c, okay, we have ds as our differential. Then inside here, we stick in a function. It could be 1, 2, or 3 variables, but we'll look at the 3 variable case, f of x, y, z. It could just be f of x, y if you're talking about a curve in the plane. And what would, so that's notation. So that's the integral over a curve c of f of x, y, z ds. That's the notation for the line integral with respect to arc length. What's the actual working formula here? Well, what does ds equal? ds, and it's important to remember what these differentials stand for. ds is the magnitude of r prime of t dt. So if you actually parameterize it, you can put in your limits of integration. T goes from a to b. And then when you evaluate these things, you've got to put x in terms of t, y in terms of t, and z in terms of t. So this is going to be your working formula. Integral from a to b of f of x of t, y of t, z of t. And then ds is the magnitude of r prime of t dt.